Gn. This new section generalizes from the geometric algebra G3 to the geometric algebra Gn. We'll start with the definition of a blade. A K-blade in Gn is an outer product of K linearly independent vectors, as shown. Another definition. The blade B represents, first, the parallelepiped in Rn with sides B1, B2, and so on up to Bk, and the subspace spanned by those K vectors. Couple of examples. The pseudoscalar I represents the parallelepiped with sides E1 and E2. That's simply the square with sides E1 and E2. It also represents the subspace spanned by E1 and E2. We've already spoken of the plane I. Second example, I have here the outer product of three vectors in G10. B represents the parallelepiped with sides those vectors, and also the span of those vectors. How geometric algebra works. Here's how. Algebraic operations on blades represent geometric operations on the parallelepipeds and subspaces they represent. We've had an example. Rotations. The vector B is the outer product of one vector. And we know that this algebraic operation on the blade B rotates it by an angle I theta. We'll now turn to a second example. Orthogonal complements. The orthogonal complement of a subspace of Rn is the set of vectors orthogonal to the subspace, that is, orthogonal to all vectors in the subspace. Here's a standard theorem. The orthogonal complement of a subspace is a subspace. The most important example occurs in R3 between a 2D subspace, a plane through the origin, and a 1D subspace, a line through the origin. The orthogonal complement of the plane is the line orthogonal to it, and vice versa. A definition. Let E1 up to En be an orthonormal basis for Rn. Then I, the product of the elements of the basis, is called the unit pseudoscalar of Gn. We used a lowercase I equals E1, E2 for the pseudoscalar of G2, the pseudoscalar of a plane. I claim that the inverse of I is given by the basis elements written in the reverse order. If that's so, then this claimed inverse times I should be 1. Well, E1 times E1 is 1, so they go away. E2 times E2 is 1. They go away, and so on up until En times En. All we're left with is 1. Now for the theorem. Let a blade B represent a subspace. Then B star, which is called the dual of B, and which is defined to be B times I inverse represents the orthogonal complement of the subspace. Here we have an example of an algebraic operations on blades, multiplying by I inverse on the right, representing a geometric operation on the subspace represented by the blade. That geometric operation being taking the orthogonal complement. Plain old linear algebra can't do this. It doesn't even represent the subspace, much less enable us to compute its orthogonal complement. Here's an example. This is the bivector, which was the plane of rotation of the composition of rotations from earlier. It doesn't look like a blade, but in fact it can be written as a blade. It is a blade, and so to take its orthogonal complement, the axis of rotation, we multiply by I inverse on the right. Finally, in G3, the cross product of two vectors is the same as the dual of the outer product of the vectors. Now in geometric algebra, the cross product is not much used. There are several reasons. First of all, the cross product only exists in R3. This cross product is defined to be a vector orthogonal to U and V, but only in 3 dimensions is there a unique direction orthogonal to two vectors. Secondly, the geometric product is part of the fundamental identity of geometric algebra. The cross product isn't. And last, outer products are preserved by linear transformations. We'll see more about this when we discuss automorphisms in the next section. Project, rotate, reflect. Geometric algebra provides simple formulas to compute these fundamental geometric operations. I'll illustrate with two-dimensional objects, but the formulas are true for any number of dimensions. Let's start with projections. We'll start with a parallelogram here, an outer product of two vectors. Here's a plane represented by some blade B, and I'll project A onto B given the projection onto B of A. And here's the formula. Reflections. Again, I'll start with A. I'll rotate A by an angle I theta, a bivector angle I theta, to obtain the rotation by I theta of A. Here's the formula. You see that it's the same formula we developed earlier for rotating vectors. And last, we'll start with A and reflect it in B, obtaining the reflection in B of A. Here's the formula. J and K are the dimensions of A and B. Notice that all of the formulas are linear transformations of A in Gn. Just look at the formulas.